Hi, everyone. Welcome and thank you for joining today's webinar titled Laser Diffraction Method Development. I'm Julie and I'm going to be your host today. Okay, so I don't want to waste you and Jeff's time. I want to quickly just toss the ball back to Jeff, but you are in this webinar again for laser diffraction method development. Dr. Jeff Bodycomb is our product line manager, who is also the speaker for particle characterization classroom series. So without further ado, Jeff, I'm going to pass the ball to you.
Great. Well, thank you very much for the introduction. Hi, I'm Jeff Bodycomb. I'm with HORIBA Scientific in the Particle Characterization Group. And today I'm going to talk about a method development for laser diffraction. So let's get to it. So kind of the overview is when you start developing a method for laser diffraction, you want to think through what you're going to do. And that would start with the goals. You'll probably choose a measurement approach. You'll pick your refractive index. You'll vary measurement settings, and then you'll test your method and be more systematic about it. This is kind of how you want to think about almost any experimental method development work, and I'm going to get into specifics when you're working with laser diffraction analyzers and some of the specific things that you'll look at tweaking as we walk through this. Okay, so kind of method development goals. There are a number of different goals you can be looking for, and it's helpful to just think through what you're trying to do or worry about. The first and kind of the most obvious is you want a reproducible method that tracks product performance. So you need an answer that changes as your product changes and doesn't change when your product does not change. A secondary goal is accuracy. I'll comment a bit why I say it's secondary later, but that's a little bit of a tricky subject because then you have to define real particle size, which I don't get into much here. Then coupled with reproducibility, if questions are repeatability, can I put a sample in and get the same answer twice? Reproducibility, can I put a sample in, measure, flush it out, measure again, and get the same answer twice? You might ask questions about resolution, particularly if you're looking for second populations in your sample. Going back to the accuracy question, are you trying to match historic data such as sieves, but with a faster, easier technique? Kind of a goal you want in mind is towards the end, you'd like some sort of structured approach or structured report to explain or justify any decisions you've made. That's going to be helpful to yourself as well as others. That kind of goes with having that data and document the process so people understand what is going on. So I'm going to start with a comparison, accuracy versus precision. You've probably seen this a number of times in experimental work. Quite often the analogy is the same as here, where you're throwing darts at a dartboard. If you have all the darts land, like in the left, in a very broad group and nowhere near your target, that's low accuracy, low precision. It means your results just show up anywhere. You could have them land in a broad group centered around your target. And so now it's accurate, but it's not very precise. And that is from run to run, you don't get the same number, but it's close to what should be the right number. Moving along, if I have a nice tight group and it misses the target, that is low accuracy and high precision. So if you have a bunch of similar numbers, but they're not the right number, that's this case. And if you get the same results over and over, and they are all the right result, that's high accuracy and high precision, which is ideally where you want to be. And kind of what we think about in method development is we start by getting the precision, and towards the once we have the precision, we usually find out we've gotten the accuracy we need, or we can kind of create an offset to get it there, particularly with a correlation. So a lot of method development discussion is this precision. Okay, so accuracy. Is it the real particle size? Well, most particles have a bunch of different dimensions. If you look at your phone, for example, there's not one number that describes the size of your phone. And so it's as much the same with particles with irregular shapes. So you're going to pick one number and say, hey, this is the real number. And you might measure a different number, particularly with laser diffraction. And your question will then become, is the number from laser diffraction close enough to the number you need to move on with your life? If you look at kind of FDA guidance, you'll see discussion of comparison to a referee technique, which is most often image analysis or microscopy. And that makes a whole lot of sense. And we do suggest that you use multiple techniques, particularly as you're setting up methods, to confirm that everything is in the right neighborhood. You can also think about things like dynamic light scattering or nanoparticle tracking analysis, NTA, or TEM for smaller particles. And sometimes people like to compare to sieving or other historical data. And sieving, of course, is the size of a particle that fits through a hole, which is probably the shortest dimension. What I'm going to suggest is you focus your work on precision, because in the worst case, if the numbers are off by more than you can handle, you can build a correlation back to your referee technique or your original measurements. Also, adjustments to analysis that for improving the accuracy of particle size, such as refractive index, are much easier when you have high precision data. And if you have low precision, it's really miserable to try to build a correlation because your numbers are just too scattered. So quick slide on image analysis. And really the idea of image analysis as a referee technique is you take a picture of your particle and analyze it, and you can also pick up the shape of the particle as well as the particle size. So here I zoomed in on a particle, and you could see it has kind of a long dimension through the diagonal and a short dimension and a different short dimension perpendicular to the diagonal. So there's no single number that can summarize that particle size and shape and everything else. For reference, laser diffraction gives you the size of a sphere that scatters like your particle. For such a clumsy definition, it's a very, very useful measure of particle size. Continuing the theme and really pushing into where I'm interested here is types of precision. So there are two ways to think about your precision. The first is repeatability. You prepare a sample, you add it to your system, you measure, you get a result, you press measure, you measure it again. You just recirculate it and keep measuring multiple times. I comment it provides limited information because it's just a test of analyzer performance and part of your method performance. The nice thing is that it provides limited information because it tells you that one part of your measurement is stable or unstable. The next step up is reproducibility. Can I load a sample into my system, make a measurement, dispose of the sample, clean everything else out, and start from scratch again with a fresh sample from the same manufacturing lot? Do you get the same number? Well, here you have other questions of sampling, of any sort of sample prep you do before adding it to analyzer. And so this is really what you want to get to as you move into things like QC work, because it's really going to tell you which lots are similar versus different. Having repeatability data in advance or having tight repeatability is a prerequisite to reproducibility. And so I recommend you start there. So here's an example of some great reproducibility results. This is an overlay of the size distribution of polystyrene latex measured 24 times. We did empty analyzer between each analysis, and the results overlay beautifully. Well, thing about these polystyrene latex stearins is they are, we understand them quite well. We know how to work with them, and they come well dispersed in advance. And so it's a fairly, we have two things that are working for you. It's a fairly benign sample, and we have a lot of experience with it. So there is some hope for a lot of materials that you can get some tight reproducibility, but not as tight as what I show here. This is kind of a champion, what you can get to with stearins, for example. So what would be good? Well, I suggest you look at some accepted stearins, ISO 13320 or USP 429. You measure 3 or more times, calculate the coefficient of variation, the standard deviation over mean at D10, D15, D90. For 13320, you want less than 3% at D50 and less than 5% at D10 and D90. And for USP 429, they are a little bit more relaxed, 10% at coefficient variation less than 10% at D50 and less than 15% at D10 and D90. There's an important caveat in all that. As your sizes go below 10 microns, you should double all of these limits, just because of the challenges at measuring the smaller particle sizes. Okay, as I mentioned before, check repeatability first, and that's by leaving the sample in the analyzer and running it multiple times. And lets you separate issues with reproducibility from repeatability, and makes the whole process, so there are more steps, but it's easier in the sense you're able to separate your problems out. Okay, another kind of concept or thing to think about in method development is if you have questions of resolution. Are you looking for small differences between successive samples? So are you looking for small differences between successive samples, say different production lots? This is going to be tied to your reproducibility. Or you're looking to detect a small amount of material outside of the main size distribution. Think about what you need, both of these, just the first, most of the second, and what your real world requirements are. Because once you know what you need to resolve out, then you can better evaluate some of your method development results to see which way is going the right direction. Okay, so high resolution. Here's 550 nanometer and 600 nanometer polystyrene latex. That's 2 separate buckets measured in separate experiments. And I can see 2 quite distinct peaks. So if I mix them into the same bucket in laser diffraction, the peaks would blend and you really could not discern the 2 populations. This is directly connected to reproducibility. So if your result is plus or minus 5%, then you can't really resolve a 2% change in your median size. And so it's so if you need to resolve changes in your product at, say, the 10% level, then you probably want your experiment, your method to have a reproducibility in the 5% or better range. And that's going to be a real nosebleed, so try not to get yourself into that trap. Another thing might be, do you need to find separate peaks? Here's a mixture of 80, 200, and 500 nanometer polystyrene latex, and we can resolve each of those 3 peaks. Note that there is about 2-fold difference in size between those peaks to make such a make such a separation. And that ratio applies even for higher sizes, say 100, 200, and 400 micron glass beads. More practically, this comes up if you are trying to identify trace impurities. So on the left, you see a size distribution of Ludox 50 at 30 nanometers. On the right, you see a size distribution of 1.6 micron glass beads. And then the center is a mixture with 0.05 weight percent of the beads in Ludox. Here, to approach this kind of problem is going to go a bit beyond this talk. The first step, of course, is creating a good method with your sample, primarily around the Ludox 50, and then adding known amounts of impurity and testing your result to see what kind of sensitivity you have, and then looking for ways to optimize that if you need to. So you have some sense of where you want to go. You have some sense of where you want to go. Next question is, do you want to run your sample dry or wet? And here wet means in a liquid dispersion. You'll want to do that if your sample is already in liquid dispersion, because then you don't have to dry it out. You may find that smaller particles, or you have smaller particles and you need the liquid to keep the agglomerates apart, or you need to use surfactants to keep the agglomerates apart. And that would all push you towards a wet measurement. Of course, if you already have a system and you don't have dry and you don't have a budget for it, that will also encourage the use of wet. If your sample is already a dry powder, if you have larger particles, dry analysis can be a lot of fun. And so you really, out of the gate, you decide which of the two you want to use for your analysis. That's step one in method development. Going into wet method development, and later in the talk, I will talk about dry. First, you need to determine the refractive index, or choose a refractive index for your particles. You'll need to choose dispersant, decide something about sample volume, set up your pump stir, add particles to the right concentration, which you need to pick, decide how long to measure, and decide if you want to add any ultrasound to break up agglomerates. So I have a whole webinar about refractive index determination. For the purposes of method development, you should be aware that refractive index really affects the accuracy of result, but not so much the repeatability. So if you're getting the same answer every time with a refractive index of 1.6, you can recalculate that data with a refractive index of 1.7, and you'll probably get the same answer every time. Look for the real component with a literature or web search or a Becky line test, or you could measure sample and very real and imaginary to see how the results change. Notice that you have to have a repeatable, you want some good data to do that. So in the beginning, you'll probably pick a real component. You'll probably take a good guess at imaginary. Towards the end, you'll go back and review those values. We do have a method expert in the software that will guide you through all this. And I'm not going to use it today because if I just said press 2 buttons, it'd be a 2-minute webinar, and that's not very entertaining. Moving along, we've decided refractive index and we decided wet, so which liquid? Well, water is easy to handle and inexpensive, so it's very popular and it's a good first choice. You would choose organic solvents when dispersion of water is difficult or if the particles are water soluble. So you have sodium chloride, you probably are not going to be having a lot of fun trying to measure it in water. And you'll have to look for something where sodium chloride won't dissolve. Poor wetting and as a surface interaction can lead to bad accuracy because you'll have issues with agglomerates and possibly issues in repeatability. You might set up some beakers with candidate dispersants, put a bit of fine particles on top of each, and see if the particles just sit on top or if they go through because of wetting, they just go straight through the surface tension. Again, there's a webinar on sampling and dispersion that's worth looking at if you want to get deeper into this topic, but your choice of dispersant is important. So you have your liquid, so you have your refractive index, you have your liquid. Now, what do we put the liquid in? Well, there are lots of different ways to have a liquid in an LA 960. There are fewer choices in the LA 350, but you want to pick one. And you're going to have a trade-off a bit in terms of volume of your liquid system, cost, and mixing ability. So the larger volume systems Aquaflow, MiniFlow both have ultrasonic dispersion on board and very vigorous mixing and stirring. As you move to the fraction cells, you have much less vigorous stirring, which keeps you from using them with very large particles. So you'll need to pick which sampling system you want to use. Most often, you'll start with whatever is available in your lab. If you're working with us on a new analyzer purchase, we can certainly guide you. Now, towards the end of this, I'm going to say do some systematic studies to decide what are the right settings. But you have to start somewhere, and you want to start somewhere close. So you want the pumping and stirring settings to be strong enough to suspend and circulate heavy particles. And you may have an issue with bubbles as you increase that, so you need to account for that. So what do? Come into a brand new system. I have no idea what the particles are going to do to me. I will fill the system. I'll add sample to say 85 or 90% transmission. I'll hit measure a couple times in a row. And then I'll look at the size. Is it slowly going down or quickly going down? Do I see particles floating to the top? If those are true, then I increase the stirring and pumping speed. Your size is going down because the large particles are settling first, and so you're just measuring the small particles in the system. And you don't want that to happen. You want to measure everything you put in. So you increase the stir and pump. Now, if you turn the stirring and pumping all the way up, and particularly if your liquid level is low, you might start to see some 100 micron particles appear and disappear. Those are generally bubbles, so I kind of think of them as bonus large particles. And you would increase your liquid level or try to reduce the stirring and pumping speed. So I would iterate through this process until I kind of got a stable result and say, okay, I'm somewhere where my sample is behaving at least reasonably well. And you want to get into the right neighborhood before you start a systematic study. If your optimum stir speed and pump speed are both at 7, just keep it both the same for sake of argument, then there's no reason to do a systematic study with 3, then 4, then 5, then 6, then 7. You can just measure 5, 6, and 7 and be done with it. So this kind of rough screening is important to get you started. And so that's what I'm talking about. Next up is particle concentration. Now we talk about particle concentration in terms of T%, which is percent transmission through the sample cell. So 100% transmission means that there's no particles and no scattering or absorption. So, and that's just pure dispersion. Laser diffraction works best in a limit of 0 concentration, if you look at the math. And so, hey, go as low as you can. The trouble is, if you go too low, you don't have enough scattering to obtain good signals, a good signals-noise ratio, or consistent results. If you go to too high a particle concentration, you'll have issues like multiple scattering that affect your results. Typically, you're looking at 80% to 95% transmission. So step 1 I've walked you through is rough out the pumping and stirring. Now we know we have the system at least giving you consistent repeatability with no settling. I'm going to clean the system out. I refill it with just dispersion, and I'm going to add sample to say 95% transmission. So just a fairly low concentration. Hit measure on it. I'm going to add another drop to bring the T% down or concentration up. Hit measure again, and repeat that several times, going down to 85% or 60%. And I'm going to plot my measured size with T% and see what changes. Is the size stable? Is there a flat range? That's where we want to operate. If you have kind of extra peaks or you see size changing with T%, your concentration is likely too high. That is, your T% is too low. The other is And you'll see in the plot on the bottom right here, at my low transmissions, I kind of have higher size values for D50. And in truth, those are probably fairly noisy. You can also see the chi-squared value is quite high. It tells me that I just don't have enough particles to make a good measurement with such a high T% or low particle concentration. So you're trying to operate in this range, which here starts at about 94.7. Once you know that range, you can actually document this series of measurements and say this is why we're setting the limits where we are. Now, all this concentration requires that I have a sample in the system that is not going anywhere because of insufficient stirring and pumping. And so that's why I want to make sure the system is circulating properly before I go and do a concentration study. Okay, duration. How long would I like to measure? Well, long enough for good reproducibility. Typically, it's about 5 seconds. In fact, it's almost always that value. With modern sensitive detectors, it's not like a long time ago. So generally, you need just a few seconds of measurement. If you do have a large or broad distribution, you may give it longer to give them all the particles time to circulate several times. You can automate the testing in software, and you can use that for robustness testing during method validation. If your size is varying at random, you can try increasing the duration or the concentration. So if you're seeing poor repeatability, then and it's poor and random, you're looking at duration or concentration. If it's systematically going down, then it's going to be probably settling. If it's systematically going up, you might be dissolving your small particles. So you can learn all that in repeatability, and that will make reproducibility correspondingly easier. Well, kind of the final step here is ultrasonic dispersion. You want to add energy to break up agglomerates in many cases, and you don't want to break the final particles. This is very similar to changing air pressure on a dry powder feeder. And I'm going to talk about that next, so I won't go into too many details here. Typically, we set this at the maximum energy, and we vary the amount of time we do it. And we look at how the tails of the distribution change. The high end should be going away if I remove agglomerates, and I should see new smaller particles appearing on the small end if there's breakage. You want to look at repeatability. Well, I suppose it would be a reproducibility question if you change the sample that much with ultrasound. But you're going to again test the system sample inside the system without rinsing at first. And the second step is to make sure that that method is reproducible. And so you're going to have to do ultrasound on a sample, clean it out, make another sample, do ultrasound. Couple notes. Do not use this on emulsions. You will change your particle size in the emulsions. If you have solvents like alcohol, you're going to be putting a lot of energy into small spots, and that's going to cause some thermal effects, and you need to wait for them to die out before you get reliable measurement results. If you do find yourself using more than about 2 to 5 minutes ultrasound, then strongly consider using external probe, which has much more power. So how do I kind of proceed with this? I get the sample in the middle range of my T% range, I think my pumping and stirring keep me repeatable, so everything looks happy there. I hit measure. Then I give it 10 seconds or 5 seconds of ultrasound. I hit measure again. A few more seconds, measure again. And I review the results. If it doesn't change that much, you don't need ultrasound. Declare victory and move on. If it is changing, you want to do ultrasound to where you think the size no longer changes significantly, or where you get better reproducibility. Again, repeating from before, if you need a lot of ultrasound, use external unit. So here's a plot of a series of results. Size goes from 74 to 66 to 62 to 59 to 56. So in this case, This happens disturbingly often. You'll find out that as you keep adding ultrasound, your size just keeps going down. And this is because at the same time you're breaking up loose agglomerates, you may also be breaking up your primary particles, and trying to find a compromise on that can be tricky. And you can see, so for some of the longer times, I have a big jump in my finds, in that gold here and that purple here, which may say I'm now into really milling my particles more than just getting rid of this right side large particle tail in the red here. You're going to plot your summary data, and here you can see how my D90 drops off fairly quickly and then starts to flatten out. I'd probably pick an intermediate spot for making my measurements, and as you'll see later, I'll probably look at my repeatability of the results or reproducibility to pick my final ultrasound ranges. Okay, now we think we've gotten everything roughed out in terms of pumping, in terms of concentration, in terms of pumping, duration, and ultrasound. Now I'd like to drain the system out, refill it, and get the same answer. So that's reproducibility. So if I refill the system and add sample, what could cause things to vary that I haven't covered yet? Well, if it's very sensitive to T% or concentration, then that could give me a repeatability issue. So let's say I set my T% range from, let's be silly, from 50% to 90%. And the first run, I add to 90% transmission. And the second run, I add lots of sample to 50%. It's half black by now, or halfway to opaque. I get two different size results. Well, then I know I need to narrow my T% range. If you have a concentrated particle sample, you could find it's hard to hit a narrow a T% range of only, let's say, plus minus 5%. So you would pre-dilute before adding. The second issue with reproducibility is sampling. So let's say I have a suspension and I mix it up, I put a drop in right away, I make my measurement, great, I have a result, let's call it 50 microns. And I set my cup down, I rinse the system, I make some notes, I pick the cup up, I draw a little material off the top, drop it in, I measure again. Well, it's gone from 50 microns down to 20 microns. Well, that's terrible. What happened is the large particles in the cup just settled to the bottom, and the second time I drew liquid out, I didn't pick any up. So what you do is ensure your suspension is well mixed and training all the particles, even the large ones that settle or large ones that float to the top. Another issue that could come up in reproducibility is if you have suspension stability. Do you have agglomeration or dissolution effects or any other chemical effects with time? Finally, this is a good time to check that your cleaning routine is good. Look at your baselines. If they're drifting up as you do repeated measurements, it means you have a cleaning concern and you want to address that early in the development process. Notice that by getting my repeatability more or less out of the way, I can just focus on a handful of reproducibility issues, and that's kind of nice. I don't have to go back and say, gee, is it sampling or is it stirring? Because remember, stirring is a problem when you have large particles. You need to make sure it's high enough. And so, but we already know stirring is more or less okay because we did it already. Okay, finally, you really want to systematically make some measurements in support of a choice, particularly if it's a, say, quality control operation where someone will do the same method over and over, and it's fairly high stakes because it's driving your manufacturing process. So you want to systematically walk through your stirring and circulation pump speeds. You want to systematically walk through your ultrasound and your T% and start building yourself a table on the right. Okay, agitation 1, circulation 1. agitation 1, circulation 3. What sizes do I get? It's from those two. Now, agitate 3, circulation 1, what sizes do I get? So you're making up this grid. A lot of why I started this conversation around what you do to roughly get in the right spot is so you don't have to make too large a grid. So you want to take your pumping up and down a bit, your stirring up and down a bit, your ultrasound back and forth a bit, your T% back and forth a bit. And then you want to write a report to yourself or some slides to yourself so you understand what you were thinking when you made these decisions. What will tend to happen is 6 months or a year later, somebody will come along and say, why'd you do X? Or you'll have a question about some funny result. And these notes will help a lot. So here's a nice set of data on reproducibility, which points to the power of kind of systematic work and keeping good records. This was size distribution by laser diffraction with 58 different methods. I have a citation at the bottom in pharmaceutical development and technology. And there was an acceptable range in the green. Notice that cutoff at 10 microns here. So I have D50 on the left, relative standard deviation on the left, and particle size on the right. And you see how the relative standard deviation goes down with increasing size. And I have a pretty hefty chunk of results or methods that aren't really acceptable per USP 429. This is not good news when you're in pharma. If you remove the points from the not acceptable region that were generated using the fraction cell, almost all of them are gone except for one. And so now you have a systematic analysis that tells us something very important about the fraction cell, which is it's not very good at mixing particles because it just has a stir bar rather than the pumping system on the solver flow. So this group, and we learned of this, so now all of our customers know the limits of certain kinds of sampling systems based on kind of very systematic method development and evaluation, and then good record keeping. So that's kind of a nice story about what you can get to with method development if you kind of keep track of what's going on. The LA960 does have a method expert that will systematically vary measurement parameters. You can look at things, refractive index, your pump, speed, your ultrasound. You can generate result graphs of these systematic experiments. And that's worth considering as you go into your method development or if you want to systematically walk through parameters. The one advice on that is you want to start things close to where your results are already working, which is why I recommend the kind of the quick tests I mentioned earlier and for much of this talk. Okay, let's talk about dry method development, which is a little bit different. Okay, first we need to get the sampling right and determine refractive index. So we talked about refractive index already. I didn't talk about sampling, but I should have for wet because it's important there. And we have a whole webinar, half a webinar on sampling and dispersion on this. You have a big container of particles, a drum, for example. You want to make sure that what you bring to the analyzer matches what is in the drum. And so being able to draw a relevant batch of particles from the drum and then make multiple samples with the same size distribution is important. You want to systematically measure at different pressures, and this is air pressure to disperse the particles. Find your optimum pressure. You might compare dry versus wet in your method as well. You'll adjust your other settings for T% and duration, really amount of material, and then test reproducibility. So here I want to talk a bit more. This is the issue with both ultrasound and compressed air dispersion. I like to wander through life with a theoretical idea. If I plot size as a function of increasing energy, the loose agglomerates break, then there's a region of stability where the extra energy does nothing to my particles, and then I start breaking my particles and the size goes down. What happens in real life is that curve is much softer. The size just keeps going down as you add energy. There is no real flat spot. And this is because dispersion, which is breaking up loose agglomerates, and milling, which is breaking up your particles, is really a parallel rather than sequential process. So in theory, I'd like to have my aggregates, I add air, they disperse, and if I add too much air pressure or too much ultrasound, they break into small particles. Actually happens is I add some air and they break up, but in addition to the agglomerates breaking up, I break a few of my big particles into a few of my real particles into even smaller particles. So once you're aware of this phenomena, you kind of have to just be, well, you're halfway there because you've realized you can't get perfection, and so you're looking for the right compromise. Here's an example of a one pressure titration where actually things kind of work out pretty well. Let's see if I can get these right. So the purple is with the least air and the brown is with the most, and I'm really just knocking out my large particles in my suspension. Here's another more concrete example that I'll walk through with magnesium stearate. And so this is a lot more pernicious than the one I just mentioned. Red is high pressure, blue is medium, and black is low. And you can see the size just keeps going down. 7.5, 8. I went 8.1, 8.6. That might be mislabeled. Well, no, okay, yeah. So anyway, let's just look. D50 goes down, D90 goes down, D10 goes down, and so basically, what you see is as I add air, it's going down. What do I do next? And the answer is look at reproducibility. I can do at 3 bar, I can do 4 repeats. I have a mean of 4.2, I'm sorry, mean of 7.5, coefficient variation 1.4%. At 2 bar, 8.2, coefficient variation 0.3%. And at 1 bar, 8.6, coefficient variation 0.6%. And so I can make a table. I have my pressure, and I have coefficient variation for D50. And you see the coefficient variation for the 2 bar is the smallest. And so that is what I would pick for my method. So this is reproducibility. So you have very good sampling in this case in a fairly narrow size distribution. If you don't have good sampling, that is, we're not putting the same thing into the hopper each time, then these results get more fuzzy. But going back to what I mentioned before, if I have good precision, I can always get to accuracy with a correlation if I have to. So I aim for the precision. Okay, T% is done very much like you did with the wet. Vary the T% and monitor results. With the dry system, you're really varying the target T%. And the system has a feedback control. LA960, HORIBA LA960 has a feedback control to keep the T% close to your target, which helps a lot with repeatability. It actually makes a huge difference. So you want to vary that setting systematically and see how the results go. Sample quantity, again, you want to monitor, vary how much material you put in to make sure you get good repeatability. So sample quantity is the analog, if you will, to measurement duration. So I'm going to recommend, if I didn't write it down elsewhere, that you run all the sample off the hopper because you can have segregation during the sample feeding process. So kind of in summary, design for maximum precision, follow the guidelines and standards. For liquid suspensions, you wet, you disperse, you investigate your settings. For your dry powder, the most challenging part is selecting the air pressure and ensuring you have representative sampling because there isn't a great way to check it independently. Systematically evaluate your method and prepare a report for yourself and possibly for your colleagues in case there are questions later. Okay, at this point, I'd like to say thank you and pause for questions. Well, this is the end of the presentation, so it's time for the questions.
Well, thank you, Jeff, for the excellent webinar. This is packed with a lot of information. So the first question that came in that uh, is, how do you choose the best dispersant and how to ensure the pH is maintained from the process in the test?
Okay, so to choose the best dispersant, I kind of hinted at it in this talk, and I have a longer talk on that. I start by looking up what other people have done to disperse this particular material, or I start making some educated guesses. For example, you like phosphates when you're working with ceramics or oxides. You might choose SDS. Sometimes you just have to systematically walk through various dispersing agents to see which one works. Okay, so yes, I'm sorry, maintaining pH. If pH is important, and in many systems it is, because that has a strong effect on the zeta potential, which we do analyze with the SC100, for the duration of a measurement, say like a laser diffraction measurement, you can just make anything up you want that's not going to eat your system, and away you go. If you are going to make a bunch of liquid in base, you might decide to buffer it instead of just using caustic. I'm sorry, just using a simple base like sodium hydroxide, because all those small molecules are not really going to affect your results except through how they affect the particles.
Jeff, can you tell us what's SZ100?
Sorry, yeah. The SD100 is a dynamic light scattering instrument for determining particle size and zeta potential. And zeta potential refers to surface charge on particles. And really, if you have a particle with a positive charge, another particle with a positive charge, they don't like to get close to each other because of the repulsion. And so what was being asked about is, well, we know, certainly the person asking the question knows that you can manipulate surface charge with pH in many systems. And so the SD100 is your tool of choice for keeping score. Of course, if you know you're always going to be good at pH 2, you can make up your dispersant at pH 2 and be done with it.
Thank you. So lean experimental plan, do you use that to investigate the various dispersant parameters?
Yes. Yeah. So I guess what I like to do is start with that kind of quick measurement to get in the right neighborhood, and then a focused systematic study. And that's a way to reduce effort. Because if you look at this and you say, well, this is a factorial type of experiment, you have a number of dimensions, and the closer you are to optimal in the beginning, the less work you're going to have to do when you do things systematically. So kind of that first half of this discussion is not going to make a statistician very happy because it's a lot of eyeballing things, but then we close out with something that's will make a statistician happy and is much more systematic and also more efficient. I hope that helps.
Thank you. That kind of reminds me of a question that came in from the last webinar. Like when it comes to method development, do you focus on the transmittance percentage first, or do you focus on the refractive index by using method development expert?
I would try to get close in refractive index, then I would get my trend, and then I would get everything else right, go back to look at refractive index with the method expert.
Thank you.
And
So you can definitely recalculate.
Yeah, so you could do everything and then recalculate all your data later if you find out there's an issue with your old data and you want to find those numbers. Because and then once you've picked your refractive index, you stay there. But let's pretend I'm starting up and I picked, I don't know, 95% T, because I always run more dilute than I'm supposed to. And I get halfway through my development and say, hey, you know what? I'm not really operating where I should be to get great data, I'm not going to be as confident in my refractive index calculations as the method expert. So I want to go back and find that regime where I have great data and then run the method expert.
Thank you. That was helpful. Okay, can you use dry dispersion for smaller particle size less than 1 micron?
Probably not. So what happens is particles like to stick together, and one reason they like to stick together is to lower their surface energy. And when you have small particles below 1 micron, they have lots of surface energy, and you really need to beat on them to get them to separate. And as soon as they touch again, they stick together. So if you can mediate that interaction with a liquid instead of air, you're much better able to separate those submicron particles. I can't really imagine a 1 micron system running well in air dispersion.
Mm, perfect. Thank you. Now, what kind of standard and dispersant are used for HORIBA laser diffraction tool?
So standards, we use two kinds of standards in our laser diffraction tools. And we actually have a talk on what was it, validation, I think was the title. But we use polystyrene latex, narrow polystyrene latex Stearates. And the nice thing about them is they're less expensive, and they're fairly quick to use. So they're inexpensive, they're quick to use, and they're a good test of your optical system. So you put in 1 micron polystyrene latex, you get 1 micron out, boom, everything's good. You know, your optics work fine. We also use broad glass bead standards, which are more expensive. Now, the reason we spend the extra money and trouble with them is because the size distribution is broad. If you have a pumping or mixing problem, then you will have the results from the standard will show up. So I put in 1 micron PSL. Wow, I get the great answer. I put in, I don't know, 100 micron. I get the perfect answer. Everything's good. I put in a broad glass bead standard, and my size is too small. And and it just consistently, I'm losing my large particles. I have a pumping problem, and so that broader standard is a great diagnostic for the pumping problems. And so we do use both in our internal quality control and qualification of the instruments. And then dispersant for both is water because it's cheap and non-hazardous. And look, you go to a customer lab, if they're not prepared to handle a flammable solvent, you don't want to be bringing it with you and inflicting all that extra safety precautions on them. So yeah, there's a pretty heavy push to just stick with water.
I like water.
Yeah, I like water too. Now, I have run all sorts of nasty organics as well. So yeah, so the system can handle it. We just don't enjoy it as much.
Perfect. Thank you. And I think now is a good time for me to share with everyone because I saw that some of you have raised your hand. Feel free to type in a question in the chat box so I can just read it out loud to everyone and address them accordingly. And if you are feeling shy, you can certainly email us at labinfo@horiba.com anytime, and I'll send that in the chat box as well. Okay, so I think that's all the questions for now. Um, for those of you who raised your hand, now is your chance.
Ah.
I don't wait for a long time. I'm kidding. I'm kidding. Okay,
I was
cool.
serious.
I know. I have a clock that's
It's
ticking a little
fine.
bit
It's fine.
faster.
And we did have some questions come in, so let's get to them.
Sure. If the RI you begin the method development with, and later you change the RI to get reproducibility result, what information do you get from it?
Okay, so if you change your RI, you're not changing your repeatability. So if I run a sample with 1 RI, I get 1 micron, and I change the RI, it shifts to 2 microns. It's just going to change all the numbers over. It's not going to affect repeatability. So the RI is really telling the math what light is doing inside the particle. Okay, so the math is getting two things. It's getting all the experimental data, and it's getting a couple numbers with the RI, and then it spits out size distribution. Well, that input of the experimental data, the intensity on the detectors, if that's always the same, you always get the same answer out. And so if I have a repeatable method, my raw data coming in is always the same. And if I change how it's calculated, my results shift for all the experiments the same way. So RI really has a strong effect on your accuracy and a weak to zero effect on your repeatability.
Thank you. Okay, so the last question is, if our particles are known to not disperse well in water, have you ever seen sonication used to get adequate dispersion?
Yes. So yes, I see that a lot. So if your particles are not dispersing well in water because they just need a little extra kick, ultrasound works great. If your particles are not dispersing well because they like each other more than they like water, then you're going to start looking at surfactants or a different liquid. So it depends on the situation. I've certainly seen systems that just 10 seconds ultrasound and everything is beautiful. I've seen systems where 10 seconds of ultrasound, the size decreases and then drifts back up because the particles like each other too much.
Thank you. On the next question, which I think will be the last question just to honor everyone's time, how can you confirm you are operating in the right RI regime?
Okay, well, a couple things. The first is you're probably going to arrive at your problem knowing something about your system and be able to either look up or measure the real refractive index elsewhere. And I go into that in the webinar. But if you're running something like something well known, I think like TiO2, you can look at the RI value. You can look at the fit to your laser diffraction data, and if your RI value is particularly poor, you can see that that fit is also correspondingly poor, which is something I referred to in the method expert before. The third is that you might use an orthogonal technique to confirm that your sizes are in the same range. If I mentioned microscopy before, and my comment there is, if you do microscopy and laser, if you do two particle analysis techniques and you're within, say, 10 to 15% of each other, that's good. If you do two particle size analysis techniques and they're within 1% of each other, something went very wrong, because it doesn't happen with anything except narrow spherical Stearates. So kind of keep that in mind as you compare techniques. So if you're in the right neighborhood, you're good on RI. If you're exactly the same, you're probably not so good. So I'll close with that bit of confusion.
Well, thank you. Thank you so much for all the good questions and for the webinar, Jeff. For now, have a great day, and we'll see you at one or more of our future webinars. Bye, everybody. Bye,
Bye.
Jeff.
Thanks, all. Bye-bye.
Thank you.